All right, welcome everyone. Once again, thank you for joining today's session. We're going to be talking about the conversion of members to meshable panels. And this is really I would say, an under-advertised feature within SRAM that's been implemented quite a few years ago now, but we've never really had a dedicated webinar on the topic. It may not necessarily apply to every project that you're doing, but it can certainly unlock some additional functionality within the tool that you're already using. So hopefully you'll find this useful. I'll start with an introduction. My name is Matt. I manage the global technical team responsible for technical support, training, webinars, and so on related to the SRAM suite of products at Altair. And I'm going to be talking to you about this topic today of converting members to meshable panels. First of all, I want to answer the question, why bother converting members to a shell mesh? And we'll look at a few different examples of building a single member model, modeling a member connection, and adding more details to your model than you might be able to represent with a 1D member element. At the end, we'll have time for Q&A, as we do in all our webinars. And I do just want to remind you, if perhaps you haven't attended the previous webinar or other what we'll call coffee break style webinars like this, it's a little different than we might have seen in previous presentations of ours. They're meant to be a little bit more short and informal. We're not going to spend too much time in the slides, more so going through the actual exercises in the software. They're also typically a little shorter than our regular webinars, which usually went 45 minutes or so. These are usually under half an hour because we know you're busy and you've got a lot of time. So we try to distill it to the content that's going to be most relevant to you. So with that, let's jump right into the examples. And I'm going to start by answering one of the questions I asked earlier, and actually an old training model that I've been using over the years. And I think it really helps illustrate one of several different reasons why you might want to go with a 2D model of this type of arrangement. I guess say 2D element model versus a 1D element model. So effectively what we have here is two different beams represented in different ways. If I render the model, you'll be able to see here that we're using the same effective cross section. Let me get the right view. One modeled with a 1D element, a member, and the other meshed with shell elements. Now, there are some nuances to modeling with shell elements that we need to consider, and that's discussed in a lot of our training content and so on. But SRAM has the capability to do both. One thing we want to keep in mind is when we're working with a 1D element, we're perhaps more familiar with the conventions and so on related to supports and loads and all sorts of connectivity. They are a little bit different with 2D element mesh because you can see here on our 1D element, we have a node at the end on the left side and the right side. And those are the only nodes that represent our member. In between, there is a cross-sectional stiffness that's characterizing how stiff this member is, and we can calculate the stiffness of the entire system based off of that. In the shell element model, we've got plenty more nodes, and shell elements with a defined stiffness and material property to characterize basically the stiffness between each end of the member. But obviously with this, we have a lot more decisions to make related to where our boundary conditions are, for example. So if I look at my supports on this structure, you can see that we're assuming that we have a fully fixed support on this one end closest to the screen here, and it's cantilevering in the other direction. So that's pretty straightforward how we would model that with a 1D element. However, with a 2D elements model, we have a lot more potential ideas and options we can test out. And this is where it may better mimic reality in a lot of ways, but perhaps won't align with our 1D element modeling conventions. For example, we've got all these joints along the edge of our beam that we're fixing here, but it poses a question, do we fix just the web? Do we fix just the corners? Do we fix only the flanges or the top flange or whatever it may be? Every situation is a little different. So it does allow you to represent more conditions than you would with just a 1D element, but naturally you do have to have more information because you can imagine how much your results might vary based on these assumptions that you're defining. And the same thing also applies for our loads. If we go to the loads window here, and you can see I've got a tip load case, and I display the joint loads on my model. I have 105 kilonewtons of basically downward facing loads on this one node at the end, which is pretty straightforward why I defined it that way. On the other side, though, we've actually loaded all the joints within the web of this member. And so this is one area where we do get a little bit more flexibility with this type of shell model, because we could go ahead and apply a load to the outside of our flange, for example. If we had a load that wasn't concentric with our member and wasn't going along the neutral axis of our member. So it does open up a lot more capabilities there to represent perhaps a more realistic scenario if we aren't living within the perhaps idealized confines of a 1D element. Continuing on with that, I've ran an analysis on this model already, and I think I've still got the results. It doesn't take that long to run, but I ran a buckling analysis. If you're not familiar with buckling analysis, basically it's an Euler buckling analysis that's going to allow us to extract the buckling modes and our critical buckling loads associated with the buckling factors. Now with this 1D model, you can see here that we're not going to be able to represent certain buckling modes the same way we would with the 2D element model. So when I actually render these buckling modes, I'll animate them here. You can see that the first buckling mode is in the shell element model, and it's what I'll call a lateral torsional buckling mode. Something that we can't really represent with a traditional 1D element model. There are some empirical approaches and so on, some that we actually have within SRAM, but this is really like raw LTV behavior that we're getting out of this. And that's just one of the downsides of not explicitly modeling our flanges and our webs and so on in detail model. We do have to simplify it to a single one. Now you may be wondering, well, how do I go about actually generating this type of model? There's a couple different ways that we could do it. If you attended the last session, you'll know that we can generate meshable panels, and we can generate them in all sorts of different planes and mesh them and produce a mesh just like this. And in older versions of SRAM, that was kind of the approach I would recommend. However, we do actually have additional abilities now. So if I just switch to another instance of SRAM here, and I'm going to drag this over. This is a blank model in SRAM. And what I want to do first, I want to define a cross section. So I don't have any cross sections defined, but I'm going to right click on the section properties tool. And with the section properties tool open, I'll click on the steel button. And everything's opening up on my main monitor on the other side here. So apologize if you see me dragging things over. I'm just going to choose a cross section. And for the sake of this demo, let's just use a wide flange shape. I'll go with a W360 by 122 section. So here's my section properties, my dimensions, and so on. I'm going to click Add To, and I'm going to click Close. And the reason I wanted to define it this way is I can now go ahead with the member definition tool, and I can make sure that that cross section is assigned. And I can simply just left click on the joint I want to draw it to, and the joint I want to draw it the endpoint to. So that's a total of 10 meters in length. And we'll be able to see here the cross section that's been assigned. Now, in this particular scenario, this isn't a particularly large cross section for the length. We could have obviously chose any section if we wanted to, but I just chose one out of illustration purposes. And we want to say that for this model, I want to go and look at what we could do to generate a 2D element mesh of this particular section, of this member, I guess is a better way to put it. So I know the cross-sectional dimensions. I also want to assign some different properties, things like supports. Here I can go to the support tool, and I'll make it easy on myself and just assume that we're dealing with a cantilevered member again. So I'm just fixing this one end of the member. And now I can go into the mesh menu within SRAM, and we have this command that says convert members to meshable panels. So I can open this command up, and it's going to give me some controls to basically produce a panel element representation of this geometry, of this cross-section effectively along the length of that member. So I have some controls. We'll look at different configurations of these controls here, but I'm not going to convert the joint to connection only. I'm actually just going to generate a panel element model of this entire member. And we can choose how many links we'd like to subdivide this member into. I'll say, let's go with 10 links. And we can also generate offsets, generate member offsets, at the connections of the member. So here we can choose whether or not we want the panel element model to go all the way to the end of our members, or we want to leave a little stub of member left over to retain our simplified member connectivity, our supports, our joint loads, and so on. So I'm going to go with these parameters here, and I'm going to click the OK button. And you can see right away rendering looks a little bit odd, but if I just turn off the rendering of the model, you can see what we're left with. So basically we've shrunk this down so we have a little bit of an offset between the member ends and where this mesh or panel element model starts to materialize. And we've also got this control that I had turned on as well. If I go back to convert members to meshable panels, I've got this control to enable warping. So I've got this toggled on, and what that does is it basically generates a rigid body constraint at the end of the member where it connects to this panel. And it's going to make sure that any rotation and so on is transferred between the member and the joints within that panel and mesh that we're going to eventually produce. Now, just like last week, if you did attend, you'll know that these panels, they are meshable panels. These meshable panels have a thickness based off of the section properties that were defined. We have mesh densities and so on. Let me just turn off some of these parameters. Mesh densities that are described based off of the length of each element and so on. And we can go ahead and we can mesh this. Now, there are some controls that we can use to control the mesh, like we can mesh just the selected elements if we wanted to, just mesh a portion of our structure. We can also choose to average the mesh density over all panels. So I'm going to turn this one on. I personally find it gives me pretty good results most of the time. And I'll turn off the display of my elements mesh densities. And then I can just click on this button right here, which is Mesh Panel Elements of type Membrane, Plate, or Shell. And on the other screen, it was showing up with kind of the meshing progress. And what we're seeing now is the output of the mesh. Now, this may or may not be satisfactory to us. That's totally fine to say this isn't good enough. I want a finer mesh, for example. So I can click the No button. And here with the Panel Element tool, I can go to this Modify command, and I can say, just modify the mesh parameters. And I want to increase the mesh density from what was originally about 3 or 4, depending on the panel. Let's change that to 10. I'll click OK and just apply this throughout my mesh, or my panels, sorry, and look at the mesh density now is 10 for all of them when I toggle this on. So I'm going to turn this off again, and I'm going to remesh. And you can see now it's produced a much finer mesh. Maybe a little bit hard to see what's going on with all my joints. I can click the Yes button though, and I can zoom in. Because I am zoomed out fairly far, it's a little bit hard to distinguish what's going on. And you can see we're now getting about 2 elements along each side of my flange, 4 elements along the length of my web. And sometimes these joints, they become a little bit of a visual kind of distraction when we have this many elements closely spaced together. So what I like to do actually, and you may have seen me do this before, is I go to the options menu and I go to joints, and you can see it's toggled on right now with this check mark. I'm going to untoggle that. And I just find this a little bit easier to see what's happening. Now we can go ahead and say, well, I want to apply some loads to this model. And because we've retained the joints at the end of our members that are connecting to this, we can simply just go in and make it easy on ourselves and say, well, let's create a new load case. I'll just call this test. And we're going to go with a joint load. And a joint load that's going to be applied just to this joint end here. And it's going to have a magnitude of -10 kilonewtons. Go left click and apply it there. And you'll see here that we have retained our joints at the end as well. Now, I could have just as easily extended the mesh to the entire length of the member, and I would have been able to then control, do I want just my webs supported or loaded? Do I want anything else to be controlled in a different way? We can also convert members, loads on members to loads on our shells. There's a utility to do that, and you can find more details on that in the help system. Unfortunately, we don't have time to go through every possible circumstance today. But let's just say for the sake of this illustration, I'm going to also apply a load, and it's going to be a little bit higher load. I'm going to apply it to the edge of my flange here. Just arbitrary location, but somewhere that I wouldn't have been able to apply if I just had a 1D element. Now I can go ahead and analyze my model. So I click on the Analyze button and click on linear static analysis. Okay, I'm going to run the analysis and it's going to ask me to save. So I'll just call this live demo. And you can see we're getting a clean solution. It did take marginally longer than a 1D element, but it's still quite fast. And now I can go to the graphical results window. I can see how my model's deflecting. Naturally, we'll see some, I would say, interesting looking deflections because I do have not only a tip load, but I have a flange load as well. So if I look at maybe one of the sides of my model, I can see that it is clearly deflecting that one direction. And I can even look at things like shell contours. So if I just switch my view here, get a 3D view, I'm able to look at things like my Z deflections, for example. And I can see where those Z deflections are highest or are lowest. I can look at things like my von Mises stresses and see what my von Mises stresses are throughout my model, where they might be highest, and maybe a better view is in order here, just so I can see the other side of my model. Naturally, where we've got our supports, we're going to see some increase in that stress as well. So that's just one method that we can produce this geometry. You saw that can be done fairly quick. Now, I was describing the process along the way. Obviously, there's a lot of different parameters that you can adjust, and I encourage you to play around with those if you see an application where this might be helpful. I do want to, though, change gears slightly, and I want to go to another model. And this model right now is represented by basically a T-intersection set of members. I've got two different cross sections assigned, and maybe I'll render these. So you can see I've got a W530 by 82 section, and I've got a W360 by 179 section. I don't have any loads or anything like that applied to this, but these could be represented with channels, with pipes, whatever it is that we want. And with this now, I could go in and I could say, you know what? I want to convert this to a mesh as well. I'm going to go to the mesh command, convert members to meshable panels. And this time I'm going to do it a little differently. I'm going to say convert joint connection only. So it's going to just focus in on the conversion of the geometry around the joints. So it's removing the ability for me to define the number of subdivisions of that member, and it's really just focusing on the joint location. And here I can say, let's generate an offset. I'm just going to generate an offset so I have a reasonable amount of panel length at the edge of each joint. So click OK. And you can see here it's generated for each joint in my selection set panel element array. Now I've got a little bit more than I need. So here I could get rid of some. I could get rid of these guys, for example, since I'm not going to really focus on those. And I'm also going to get rid of my other elements here and my extra joints. So I'm left with basically just a fairly simplified model. But then I could go in and I could say, let's just mesh this guy as well. I'm going to go with mesh panel elements of type membrane, plate, or shell. And it's going to produce a mesh for me. Again, just like before, I could control the density. So this might not be dense enough for my liking. I can click the no button and I can increase the density the same way I had before. Just go with modify mesh parameters and let's increase this mesh density to 15, let's say. And we have full control over this model, so we can adjust it as we need to. We can move things around and produce a nice quality mesh. SRAM has really powerful meshing algorithms, and we'll be able to run an analysis on this model when we apply loads and so on. What's also handy is if you come up with maybe a, let's say, pipe section, for example, or an HSS section, where the members are going to be each connecting at the center line, but naturally the material of that element is adjacent to the center line. So you're going to have some overlap of material that you would actually need to trim out. Panel, connecting panels, and that you need anymore. I actually use that quite often when working with circular sections, for example, or HSS sections that might need a bit of trimming. It's very easy to do, and I can produce this. Now, my notes that I kind of work with to describe what I'm going to show and when I'm going to show it, I did also have one thing I glazed over here that I want to touch on. Obviously, there is value in having a 2D element mesh to represent this this type of geometry. And we can look at a lot of interesting results along the length of the member, like there's moment contours, shear contours, and so on. However, it may not necessarily always be that we want to totally depart from the 1D element results as well. So what we can do actually is we can say, well, you know what, I want to go to what's called the wall. We can left click and we can configure it to look at options. So there's the ability to look at, which is helpful for working with like wall elements, for example. But if we're working with a member that's converted to a mesh, the diagrams option is a lot more helpful, I find. And it's going to allow us to look at things like the moments, consider you or a traditional 1D element with section lines or wall elements in this model. It's generated for you automatically. Okay, the last thing I want to touch on in this presentation here is probably worth actually creating a new model for. So I'm just going to really quickly generate one with the equal spacing 1 meter grid. I'll say that we have a, I'll say it's an 8 meter long member. I'm going to sake of for continuity. And let's make this a W650 process one, maybe not so 800, let's say. Not a realistic scenario, but just one I wanted to throw together for illustration. So click OK. And here we've got our cross section assigned. I'll give it a color. And I just want to render this just so you can kind of get an idea for the scale and so on. And as you can probably guess by now, I'm going to convert this to a meshable panel. So say convert to meshable panels. I'm not going to convert it to, for the joint connection model. I'm actually going to keep it as a member model. I'm not going to worry about enabling warping or anything like that. Here, I'm just going to say I have 8 links, and I'm not going to generate any offset at the member ends. So click OK. And what we can see here is it's generated for us this panel element model, just like we had before. And now I can go in and I could add additional details to this model. So here, I might actually want to change my grid, for example. So here, I'm just going to say that I have a grid, create a new one. And this grid is going to just be useful for adding details to my, my geometry. I'm going to call this web grid. And in the x-axis, I'm going to have one grid line at x equals 0. And I'm going to have another 8 grid lines at x equals 1 meter increments. And then the same thing here for the y-axis, 1 at 0. And maybe I'll do one more at y equals 1 meter. Click OK, displaying the grids. And so far, it may seem a little bit odd why I went through the trouble of doing this, but the reason I wanted to do this here is I can actually set up a new user coordinate system that will align with my orientation of my web. So I'm just going to define it using the 3 points method here. And you can see now I've got this grid where I've basically aligned it with this, this web at the center line of the web. And I'm going to save it, call this UCS web center. And the reason I'm doing this is now we can go to the panel element tool. And with the panel element tool, maybe I'll just look at the downward facing view. I can use the panel element tool to help me generate geometry, like a circular panel, for example. We call it circular drop panel because most often these are used for drop panels and slabs and so on. But then I can give it a name. So here I can say, let's give it a name, or a radius, sorry, a radius of, can't remember the dimensions, but let's just say 0.2 meters. And I'm going to have 8 divisions to represent this circle. And I just need to left click to apply it. And I can do this at different joint locations in my model. And one thing that I didn't do is I didn't define this as a hole. A hole panel is going to be helpful for this scenario. Oh, I was a little heavy-handed with this, so let me just make sure I've got this all defined. I can always go back and adjust them. So I'm going to go back here to my shell mix mesh panel and just make sure everything else is the mixed mesh type that I had originally applied. And if I were to run an analysis or run a mesh on this now, it's going to counter those holes and it's going to allow me to basically avoid them with the mesh to generate like a castellated beam or something like that. I can then say, well, let me just also crank up my mesh density because I found that that worked pretty well for me, having maybe a mesh density of 10 or so. So I'll apply this throughout my model. And now we can mesh. And I can click the mesh panel elements of type membrane, plate, or shell. And it's generated a mesh for me. I'm going to click the yes button. And as you can see, it's a decent looking mesh, considering I haven't really reviewed any of the parameters in advance. So I got a little lucky there. And it's generated those with that whole panel considered. So now I could go in and I could apply some boundary conditions to the end of this. Let me just switch back to my original global coordinate system. And I'm going to fix just one end here. We're doing a lot of cantilevers today. And I'm also going to apply some loads here to the end. So let me just do it here, make it really simple on myself and say, test once again. And if I wanted to, this could be a joint load where I apply a load to a joint, or it could be a pressure load. We could have a dummy member and apply a member load as well. I'm going to say that this is going to be in the global Z direction. It's going to have a value of negative 2.5 kPa. And I'm going to apply that just to a couple of the shells on the top kind of edge of my model, as you can see. And now if we go ahead and run our analysis, a linear static analysis, I got to save this as well. I'll call this. We're going to be able to get our results. Now, it seemed like I did have some issues with rigid body behavior, which I'll need to investigate a little bit more. But let's just take a look at the results that we're getting out of this. Sometimes when we do things live, it doesn't always go perfectly smooth. But naturally, we are getting some results. I can see here, my displaced shape. I can look at my shell contours and I can see where that load is applied naturally has higher moments on it. I can see the Z deflection. So we're not really getting that much in the way of deflection. But it's giving us some kind of useful information to review the behavior of this model. Here, von Mises stresses, and naturally we do see some concentrations around those holes as well. So it allows us to study these types of more complicated geometries within the same environment that we would still be able to do the 1D element modeling, all of our code checks and so on as well. So that was a quick kind of overview of some of the technology. There's plenty more that we can dive into, but we don't have all day, unfortunately, for the webinar to cover every scenario. I did want to open up the floor for questions. Maybe while I'm looking at the questions that came in, I'm also just going to point out here that if you're curious about any of these features, go to the help menu, contents. You'll be able to find a lot more information. So here you can search for a connection. For example, there's a lot of information unrelated to this type of connection here, but I can say convert members into panels, and this has a whole whole basically help system topic on this exercise that we went through today that goes into a lot more detail regarding the conversion of joint loads, warping restraints, and so on, member offsets, and more. So I encourage you to take a look if you're interested in that sort of thing, and hopefully you'll be able to find some useful details there.